Alright, we're going to look at some graphs of polynomial functions and use some important features of the function to write down an equation of the function with the lowest degree as simple as we can that would display basically that behavior. So here's number 37 from our textbook, page 150. And we've got this, it to me looks like a polynomial function because it's got this unbounded in behavior. It's smooth and continuous. I recognize it has two turning points, so it has to be at least degree 3. And because in one direction the outputs go to negative infinity and in the other the outputs go to positive infinity, it's going to be an odd degree polynomial. So it's going to be an odd degree polynomial function. And we've kind of gotten used to what the typical parent function behavior looks like. So it looks like the leading coefficient, well, I'll let you decide, is the sign of the leading coefficient going to be positive, or will the sign of the leading coefficient be negative? Okay, since the right arm is going up, it's going to be positive. Well, I hope you can see in this picture there are 3 x-intercepts. -2, -1, and +2 are x-intercepts. And the curve goes through the intercept. It doesn't just touch and bounce back. Another way, the turning point of the curves, you see them? They are not x-intercepts. So through each of the x-intercepts, the curve goes on through the x-axis. So that means each of these are going to have odd multiplicity. Each 0 will have odd multiplicity. And since we want to write down the simplest equation we can, we're going to just let the multiplicity be 1 and assume those are unique linear factors. Alright, so let's call this polynomial f. We want to write it down in factored form. That's the easiest form to write down when you know the x-intercepts. We know the leading coefficient is positive, but we don't know what it is. We know -2 is an intercept, so x plus 2 is a factor. Likewise, since -1 is an intercept, x plus 1 is a factor. And since +2 is an intercept, x minus 2 is a factor. And I'm going to use an understood multiplicity of an exponent 1 for each one of those. And I've got a pretty good expression for this polynomial. The only thing I'd like to know now is what's a. And so to complete this answer, I'm going to look back in the graph and find the y-intercept. If we can find any other ordered pair on the graph, we're good. But we can recognize the y-intercept pretty easily. 0, -8. Aha! So if we plug in 0 for x, and over here on the right-hand side, plug in a 0 everywhere there's an x, this right-hand side will be an expression in terms of a, and we'll set it equal to the output -8. So again, if we evaluate f at 0, we don't plug in 0 for a, because that's an unknown, but we'll plug in 0 everywhere there's an x. Well, f of 0 we were given in the graph, that -8. And if we take -2 times 1 times +2, I think we get -4 times a. And solving for a, dividing both sides by -4, we see a is 2. And so that tells us what our leading coefficient is. Okay, so our complete answer, using these calculations, the curve for 37 should be generated with the function 2 times x plus 2 times x plus 1 times x minus 2. And maybe we could stop the video here and type this into y1 in our technology and just double check. We do know that -2, -1, and 2 are going to be the intercepts. That's just algebraically true. The leading coefficient is positive, so we get the right arm of the curve going up. We're rising to infinity. And we don't know how far the turning point goes down, but you know, you can see if that looks pretty close. This is what they were wanting right here in the examples in your homework. Okay. Now, would you want to maybe pause the video again and start over on number 38? Okay. Well, 2 turning points. So this is going to, we can make this a degree 3 polynomial. It's an odd degree. The left arm is going up this time. So the leading coefficient is going to have a negative sign. Okay. What are the x-intercepts? Okay, looks like we've got just 2 of them, -2 and 1. And -2, you've got the curve crossing through the x-axis. So -2 is going to have an odd multiplicity. We'll just let it be a unique factor. But something different's going on here at +1. The turning point is the x-intercept. So the curve looks like it touches and then bounces away from the x-axis. And that tells us something about the multiplicity of that intercept. The x-intercept 1 is going to have an even multiplicity. So our curve, we might call this one g of x. We don't know what the leading coefficient is, but it's going to be negative. But we know the factorization otherwise. Since -2 was a 0, x plus 2 is going to be a factor. Odd multiplicity, so let's just let that be 1. We're going to make the simplest factorization possible. And then 1 isn't a 0, so x minus 1 is a factor. And we've got that bouncing off feature, so we need an even multiplicity. So we're going to let that be degree 2. And the degrees 1 plus 2 add up to 3, and that's the lowest degree polynomial that would exhibit this behavior. Though there'd be other answers. And then to complete, writing down an expression of a polynomial that would exhibit this behavior, we would need to find a, and we want to use the remaining clue. We see that there's a y-intercept of 0, -6. Okay. So if we evaluate g at 0, we expect to get an output of -6. Okay, plugging 0 everywhere there's an x, we'll get 0 plus 2 times 0 minus 1, -1 squared, which is just 1. And we get the product 1 times 2 times a. 1 times 2 times a is twice a. But we're given what g of 0 is, that's -6, so we can solve for a. And we knew that was going to be negative. All right, so plugging in -3 for a will complete the polynomial, writing down a polynomial expression that would exhibit the behavior in the graph. And you might want to check that in your graphing calculator.